We now are going to return to our discussion about power. I want to remind you about this chart that we looked at before, where we had that either the null hypothesis is true or false. And then based on our data that we collect, we will either reject or not reject the null hypothesis. Now, if the null hypothesis is true and we cannot reject it with our data, then we will make the correct conclusion. And if the null hypothesis is false and we reject it using our data, we will also make the correct conclusion. But if the null hypothesis is rejected, but it turns out to be true, remember that that's a type 1 error. And that happens with probability alpha. Of course, if the null hypothesis is false and we cannot reject it, we call that a type 2 error. And we labeled that beta. Now, if we cannot reject the null hypothesis and it's true, that happens probability 1 minus alpha. And if we can reject the null hypothesis when it's false, that happens with probability 1 minus beta. And that is what we defined to be the power of the test. So we define the power of the test to be the probability we reject the null hypothesis given the alternative is true. And that is 1 minus beta. And given a fixed alpha, we said before that we want to maximize the power of the test. Maximizing the power of the test, of course, is going to minimize the type 2 error. Since in this situation our alternative hypothesis is true, we want to think about power as being a function of a particular alternative. We'll call that alternative theta sub A. So power we can think of as being 1 minus beta as a function of our alternative that we'll call theta sub A. You can ask a question such as, what is the power of theta sub 0? That would be the probability that we reject the null hypothesis, given theta equals theta 0, or H0 is true. But that sounds a lot like our definition of type 1 error, or alpha. So the power of theta 0 is actually alpha. So let's look at how to define this power as a function of theta sub A by using an example. And the example that we're going to use is that we're going to consider a random variable y, which has a uniform distribution from theta to theta plus 1, but theta is unknown. And we're going to consider a null hypothesis that theta is 0. So if theta is 0, we're really going to be looking at a uniform distribution from 0 to 1, or an alternative that theta is bigger than 0. And we're going to choose a rejection region of y being bigger than 0.95. So what we're saying is that if the null hypothesis is true, then we have the probability density function of 1 between 0 and 1. And we're going to make our rejection region 0.95 so that the area above it is 0.05. And what we're saying is if we draw a number y from this uniform distribution from theta to theta plus 1, and that number is bigger than 0.95, then we're going to reject the idea that theta is 0 because there's only a 5% chance in that case that theta was 0. So alpha in this sense is the probability that y is greater than 0.95 when theta is 0. And we just said that that probability is 0.05. Okay, so that means that the power of 0 as an alternative is 0.05. Now, what is the power of an alternative of 0.1? So let's suppose in this case that 0.1 is, or theta is 0.1. So I'm going to draw a little picture off to the side here of what happens. Okay, so theta is now 0.1, and so our probability distribution is non-zero between 0.1 and 1.1. Okay, so there's our probability distribution. Okay, and then our rejection region is going to maintain at 0.95. And so the area there is 1.1 minus 0.95, which is 0.15. So the probability in that of being in that rejection region is 0.15, given that theta, our alternative, is 0.1. And so from this, we can actually use the same ideas to calculate other values of power for other alternatives. So if power of 0.4, for example, would just be 1.4 minus 0.95, and that would be 0.45. Or power of 0.7 would be 1.7 minus 0.95, and that would be 0.75. What would power of 1 be? So let's say theta turns out to be 1. What is the power going to be? Well, if we keep this along 2 minus 0.95, that would give us a probability of 1.05. Oh, but that doesn't make sense because the power can't be any bigger than 1. So in this instance, maybe the power is just 1. And that makes sense if I draw a picture and I plunk down 0.95, but theta is going to be 1. And so I have, there is my probability distribution. There's where it's non-zero between 1 and 2. Okay, and so the probability of being above 0.95 is actually just 1. Okay, well, we can actually now define a pattern. You can see the power of 0 was 0.05, the power of 0.1 was 0.15, the power of 0.4 was 0.45, power of 0.7 was 0.75. That looks like it's got a pattern there. What is the power of our alternative? Well, it seems to be our alternative theta A plus 0.05. But when's that going to work? Well, that'll work as long as theta A is between negative 0.05 and 0.95. Remember, we got above 0.95, and then the power was just 1. So that means, similarly, if the power is going to be 0 if theta A is going to be less than negative 0.05. We can actually draw a picture of this power function. We can draw a graph. Okay, so I'm going to make that 1. 0.95 is kind of important on this graph. Negative 0.05 as well. Okay, and I'm going to draw this function in red. Okay, it's going to be 0 up until negative 0.05, and then it's going to be linear with slope 1. It's going to grow until I get to 0.95, and then it's going to be 1 after that. And so this is my power function for this example, theta power versus theta sub A, the alternative.